Friends, happy morning, Shubham Jani, good morning. Hope previous class we did one small derivation and also discussed on the result. I'm sure that you've gone through that and you are ready with all those results. Now today's class will do another case of finding potential due to dipole. Now the concept of dipole we have discussed much earlier. Therefore, I need not remind you all those things now. You can go back and watch it. You will find all those terminologies. What is dipole? What is axial point, equatorial points? What is dipole moment and all. Now here we are taking actually the case of short dipole. Even that short dipole we have used it in the earlier cases. What do we mean by short dipole? The dipole in which the length of the dipole is negligibly small as compared to the distance of the given point from the dipole like that. So this is the case of potential due to short dipole. Now, see, everything is ready here. This is what is the minus q plus q, a system of separation with 2a. This a, b, this separation is what is 2a for a mathematical convenience. Therefore, this AO and OB will be equal to A. Now see here AO bar is equal to OB bar. This magnitude is equal to AB. So this is a dipole of length 2A and O is the center. Dipole moment. Dipole moment, you remember, always a vector from minus q to plus q along the axial line you said. Therefore, this is what is the direction of the dipole moment P bar. Right? This is a dipole of length 2a and a dipole moment P bar, and P is some point because when we did the case of electric field, you remember, we did separately for electric field at axial point and equatorial point, all such things, is it not? Now here we will do a generalized case. We just don't do it for, we can also do like potential at axial point, potential at equatorial point. We are not doing that method. In fact, we are doing a generalized method. In that, from that result, you can write potential at any given point. So that is what is the approach here. So P is some point which is at a distance R, but I have taken this OP bar as a vector R bar. The magnitude is R, and this angle is of course theta with the axial line. So P is the point of observation at which now we are finding the electric potential. Now, see. Now you can make two to three simple statements as well. Let us consider a dipole of length 2a and dipole moment P bar. And P is a point of observation at a distance R, making an angle theta such that this radius vector makes an angle theta with the axial line. Now I am writing the simple. Because I have told you earlier also, remember, derivation means always the first line which is very important. What is the change that we'll do in second line and so on. So at position P, see, this P is at a distance R1 from which charge? This negative charge, and it is at a distance R2 from positive charge. Therefore, at the position P, the potential is due to this negative charge, which will be negative, and potential due to this plus Q at P, it will be positive. So therefore, there will be two potentials caused by minus Q and plus Q at P, which we are writing separately. At position P, V due to plus Q, V due to plus Q, or else I have taken this R1 is not. So I will write it down. Let me take this as some R2, let me write this as R1. Whichever is okay, but I think your textbook has given you like this. So when you follow the textbook, it makes you easier. Therefore, V due to plus Q, V due to positive charge is potential due to point charge, 1 by 4 pi epsilon naught, Q the charge by distance term. Therefore, now what is that? V due to positive charge, 1 upon 4 pi epsilon naught. The charge is Q and the distance is R1. R1, and it is positive. Remember, this is a positive potential because the charge is positive. And what is the potential due to negative charge? This is 1 by 4 pi epsilon naught, the constant. The charge is of course q, which is minus q, and the distance you see here, this is what is R2, and this is a negative potential, earlier we had told. So this is minus q, and therefore it is a negative potential. Therefore, V net at P, the net potential at P is equal to, yes, I have told you it is the algebraic summation of the individual potentials, what our definition. Therefore, our principle, therefore we are writing as 1 by 4 pi epsilon naught. This is common. This q is also common, is it not? Okay, first let me write that. So this is V due to plus q plus V due to minus q. Right. The two potentials are added. And of course this is an algebraic addition. Therefore, the result is V at P is equal to, what is VQ and V minus Q? See, this Q by 4 pi epsilon naught term, a constant, common term in both the expressions. Therefore, Q by 4 pi epsilon naught times 1 by R1 minus 1 by R2 we have taken. Why that 1 by R1 minus 1 by R2 you see here? You see here? Because this is negative potential. Therefore, here this comes the negative sign. Now I call this as equation 1. This is equation 1. This is equation 1. Now this is where this is one milestone you can say, writing this value. After that, see, look here, 1 by R1 and 1 by R2. Our final answer should be in terms of R. Therefore, that 1 by R1 and 1 by R2, that evaluation is what is the remaining portion of our derivation. Right? For that part, what we do is we will make use of 2 points, two mathematical tools, I will say. The first one is a triangular law of addition, and the next one is, of course, a small binomial expansion. Binomial expansion. So these are the two things that we are going to do here. And that is why everything now here is represented in the form of vectors. In the form of vectors. Now, you see here, you will find two triangles. The first triangle is AOP. One triangle you will get. Another one is OBP, triangle that you are getting. You remember what is triangular law? A very detailed discussion in first PU we did. In that triangular law, I have told you the rule as AB, BC. See, AB, BC, one order is there. Whether clockwise or anti-clockwise, one particular order is there. AB, BC, the answer is AC we told. AB, BC, AC is the result. Let me show you here this. Now this see here, AO, suppose one vector, AOP. You are getting it as AP. AOP, the answer is AP. Similarly, the other triangle also. So for that triangular law, what is the resultant? We have told in the first year, R is equal to root of P square plus Q square plus 2BQ cos theta. The same I am going to use there. Right? So now what I do is that from the geometry, using triangular law of addition, what is that you can write? See, AOP is equal to AP. Therefore, now I can write it as R2 square is equal to, right? What is that? A square plus R square plus 2AR cos theta. Is it okay? A square plus R square plus 2AR cos theta. I have squared on either side. Supposing if this angle is what is theta, then this other angle becomes 180 minus theta. Cos of 180 minus theta becomes minus of cos theta. Therefore, this is R2 square is equal to, is it? Now similarly, we can write it as R1 square is equal to same A square plus R square minus, because cos of 180 minus theta term, this is minus 2AR cos theta. So these are the two results using triangular law of addition. Now from these two things, just making use of a small simplification is there, which I will do in my next board. See for that. See this equation 1 is potential at point P in terms of R1 and R2. And we have this relation R1 square is equal to R2 square is equal to, is it not? Now let us do a small simplification for this. Please take it for take it as a very important point that derivation you should use with common sense, which you call mathematics. Here in this expression, what we do is we take R square a common, then it is 1 plus, right, A square upon R square. R square is taken as a common factor. Then this is minus 2AR upon R square, which you will get it as, yes, 2A upon R times cos theta. This is the result that you get, is it not? Right? This is, we are writing it for R1 square. Now here comes the case of short dipole. Earlier we told that short dipole, the condition is small a, which is half length. Whenever you are using this term a here, this is not the dipole length. This is half length of the dipole, because we have taken 2a the dipole length. When we are taking this point P such that R is much greater than this dipole length, then this A square by R square is too small, and therefore we neglect this term. So this is an approximation that we are taking, which is justified for short dipole. So the same we are writing for short dipole. For short dipole, that is, I will write again condition A very much less than R. A itself is less than R, means A square will be too small as compared to R square. That is our justification. A very much less than R, such that A square upon R square is negligible. Therefore now I just ignore this A square by R square. Then the equation will be like R1 square is equal to R square times 1 minus 2A by R, 2AR of course cos theta upon R. This is whole under root. Therefore I will write some R. See, this is what I am writing. Right. So R1 square is equal to R square times 1 minus 2A cos theta by R. This is power half, which means square root. No. This is only 2AR. Now here I am writing it as R1 is equal to R1 equal to, yes, R square becomes R. And here you get this 1 minus 2A cos theta by R. Now you get this power half. R1 is equal to. Now I want 1 by R1. In this expression you have 1 by R1 term. Is it? Therefore I will write it as 1 upon R1 is equal to 1 by R. This becomes, you see, this becomes 1 minus 2A cos theta upon R whole rise minus half it becomes. Because we have taken the reciprocal, this half becomes minus half. So in each and every step, what is that small change that you are doing, focus on that, then it is not memorable. Now you see 1 by R1 final expression I am writing using binomial expansion. In that binomial expansion, let me tell you the principle which we have used in physics many times, and also in the coming Weeks and months also will make use that in many such simplification. What is that? 1 plus r minus x whole power n. Remember, 1 plus r minus x whole right n. For now condition we are writing x very much less than 1. This x is very small as compared to this. So x very much less than 1. For x very much less than 1, we are writing the condition as this is 1 plus or minus nx. Because we consider only in the binomial expansion, only first term is taken and all the other higher order terms, earlier we have seen there, a square by r square. If you get it as a cube, then it is further negligible. Therefore, higher order terms are neglected. You get this 1 plus or minus nx. One more time. 1 plus or minus x whole rise n is equal to 1 plus or minus nx. You are multiplying this with this index. You follow here the same because we have taken the case of a short dipole. For a short dipole, this a by r is very much less than 1. Is it not? Short dipole, a by r is very much less than 1. Therefore, I can make use of that binomial approximation. Therefore, this is 1 upon r1 is equal to 1 by r times, yes, this is 1 minus of, shall I write, minus of 1, this is minus of times 2a cos theta by r. 2 gets cancelled, this minus of minus becomes positive. That is how you do. Is it okay? 1 by r1 is equal to, this is binomial expansion. The 1 upon r1 is 1 by r times, this is 1 plus a cos theta by r. A cos theta by r will be 1 by r1. It will be 1 by r1. Now, similar treatment we can also do it for r2 square expression. The similar result we will write it for 1 by r2. Now, again, I want one more board, is it not? Look at this point, we will write 1 by r2 and then simply substitute in the equation 1. This is the result we got, right? 1 by r1 equal to 1 upon r, 1 plus a cos theta by r. Similar treatment for r2 square also. Therefore, now we will write the result. Similarly, you remember in the r1 square term, remember r1 square term, you got that negative sign. r2 square term, you got a positive term. Minus 2a cos theta plus 2a cos theta. Therefore, if it is here 1 plus a cos theta, similarly, we can write it as, similarly, 1 upon r2 is, yes, 1 by r times, it becomes 1 minus a cos theta upon r. Is it not? This is 1 by r1 if you call this as equation 1. Yes, this is equation 1. I call this equation, some number a and b I will call, suppose. You call 2, 3, whatever it is. Therefore, now what I do is that substitute a and b results in equation 1 final result. What is that? So this is V at P is equal to Q upon 4 pi epsilon naught. Again the common term is 1 by R, 1 by R. Therefore this R is a common term and within the brackets, yes, V at P is Q by 4 pi epsilon naught r. Within the brackets, what do you get? This is a cos theta by r minus of, and here you have, that also, yeah, 1 plus a cos theta by r minus of 1 minus a cos theta by r is the bracket term, right? This is the bracket term. The 1 minus 1 gets cancelled. This is a cos theta, negative of negative plus a cos theta, right? So that simplification you can see here. So this is q by 4 pi epsilon naught times, this is 2a cos theta by r. Is that okay, friends? Q upon 4 pi epsilon naught 2a cos theta. One more r is there here. Yeah. 4 pi epsilon naught r. 2a cos theta by r. Here we are rearranging the terms for the final expression. This is also a result. In fact, the rearrangement of terms is made. How? This is say 1 by 4 pi epsilon naught one term. This is 2a times q is there, right? This is 2a times q is there. This is what is a very tool for our dipole. Length times the charge, dipole length times charge. This is what is dipole moment. Therefore, 2a times q, this is r times r, becomes r square, and of course cos theta term is there. This is what is we at p. Now, finally, one more expression, and let us understand that result. The same. Here simply I make it as 2aq becomes p cos theta by r square. Let us see that. Friends, the final result, potential due to short dipole at any point, we have this expression V is equal to 1 upon 4 pi epsilon naught p cos theta by r square is the expression. Now let us understand at least a few things regarding this expression. Any expression once you got, when you analyze that expression, your understanding will enhance, then memory becomes knowledge. Otherwise it will remain as a memory only. In this expression, you remember this point P that we have considered is neither an equatorial point nor axial point, some general point that we have considered such that this line joining this r bar making an angle theta, this theta is with axial line. This is an important thing. So theta is the angle with axial point, right? Therefore now we write few special things, right? Like what? Now I am writing it as case 1, theta equal to 0 degrees. Theta equal to 0 degrees, or I will take it as 180 degrees. Theta is equal to 0 degrees or 180 degrees. Because here if you take it as theta, right, the clockwise angle, anti-clockwise angle, like that. Supposing if the point P, I'm just showing you here one more time. Supposing this is what I show. Yes, this is suppose plus q and this is minus q. This is the axial line. If you consider a point O P here, P1, and write it as here one more point, I will write it as P2. Then what does it mean here, you see? Because it makes a sense. Suppose whatever answer that we get, what is the meaning of the answer is important. Now for point P1, because this is what is the vector I have taken, this is what is P bar. Look at this point P1, I will take this angle as 180 degrees, then that cos 180 becomes minus 1. Whereas for this point P2, this angle theta is equal to 0 degrees to get, then cos theta is equal to 1, which makes a difference in the positive potential and negative potential. And what is that meaning of the positive potential, negative potential? Let us see here with respect to dipole. When we are writing, these are, see, very meticulously I'm just making you to look at these results. For theta is equal to 0 degrees or 180 degrees, this is what we get, V axial. We get V axial. Axial point we get. Such that V axial can be two ways. How? This is what is 1 by 4 pi epsilon, if I call it as K. P, this will be K P by R square, which is positive, or it can be minus, this is R square, this is minus Kp by R square. Two cases are possible. Now I will show you for which is positive and which is negative, because here you see, whenever you consider a dipole and axial point, when you consider, suppose if you consider a point over here, the axial point, it is nearer to positive charge and farther to negative charge. Any axial point is nearer to Suppose if you consider here the point, axial point, nearer to positive, farther to negative. Therefore here, positive potential is more than the negative potential. Supposing the other time you take, suppose here you take, this point is nearer to negative charge, farther to positive charge. In such case what happens? Again, the net potential will be negative. Therefore, whenever you take potential dipole, it can be either positive, negative or even zero. Mathematically speaking, cos theta, theta less than 90, cos theta positive, exactly at 90 it becomes 0, and 90 to 180 it becomes minus. That mathematical result, how we understand here. So when do you get positive potential? Yes, if the given point is nearer to axial point, nearer to positive charge and farther to negative charge, at that point the net potential is positive, or the other case, the given point nearer to negative and farther to positive, the net potential at that point will be negative. Therefore, here two cases are possible when you are writing V axial. And case 2 I will writing, see here. What is the case 2? Theta is 90 degrees. Theta equal to 90 degrees means. Now this is what is the axial point that you get for these angles. 90 degrees means, you remember, this is what is earlier we have taken the geometry. The terminology is equatorial line. Therefore, theta is equal to 90. You get it as equatorial point. Equatorial point. Now you see, mathematically cos theta, cos 90 is 0. Therefore, potential becomes 0. Potential becomes 0. At any equatorial point of dipole, net potential is 0. Let us first write the result and let us analyze why is it so. If now here I am writing V equatorial is equal to 0. V equatorial equal to 0. Why is it? Because it's a natural consequence. What is that natural consequence? Here I show you. Supposing this is the axial line, yes, plus q and minus q, and this is what is the equatorial line, yes, perpendicular to axial line passing to the center. Now you consider any point over here, which is any, see, earlier we told axial point or any other point other than equatorial, if it is not equidistant from both the charges. Plus q, distance from plus q, distance from minus q are different. Whereas for any equatorial point, see here, the distance from plus q is same as distance from minus q, because this is the angular bisector. Therefore, what happens here at P, at the point P, V due to positive charge is equal to V due to negative charge. Here, this potential due to positive and negative charges being equal, net potential becomes 0. So that is what is the point. So net potential at any equatorial point is 0. Is 0. An important result to be remembered. Remember, at an equatorial point, field was non-zero. Is it that you have given the statement as P Kp cos Kp by r cube term is there earlier in the case of field. So for the potential, what you got? V equatorial is 0. Now again, one more important, we can discuss many things, but point is, one after the other, at least a few things you look at this. And most important, V, in the case of dipole, V proportional to 1 upon r square. V proportional to 1 upon r square. In the case of point charge, you got V proportional to 1 by r, you got, whereas here you got V proportional to 1 by r square. One more important result to be found. So sometimes different distances, points at different distances, points and also angle is also there. Therefore, when you write for a dipole, when an example is given in CET or NEET or even in JEE, for a dipole, one result, what is that you can see from here? Supposing for a given dipole, two different positions, comparison of a field, comparison of potentials, when such is an example, then you will write it as V1 by V2 at two different positions due to same dipole. Then you are writing the same dipole means you expect P being the same one, common one. Here you write it as cos theta 1 by cos theta 2 times R2 squared by R1 squared. Is it not? See, these are all the common sense things that we need to do for each and every expression. Derivation over with a mathematics, what you call, or common sense, what I call. After that, look at the result. LHS terms, RHS terms, the constant terms, and what type of relation they bear. After that, supposing whatever changes that happen, this is what is a question is all about in any of the examinations. Supposing these are the changes that are happening, then what type of changes you expect in RHS, or changes in the RHS, what is the change that is possible in LHS. If on these lines you make your daily practice, that is what is the preparation for your examinations. Number of times I have told you, remember, this is an occasion I want to make you to repeat that. So what is the difference between PU preparation and competitive preparation? Many students keep on asking. They ask it even after second PU or just before seat examination. Rather, your teacher has told you every day basis. Remember, the syllabus is the same. For seat exam, board exam, you name any examination, the syllabus is the same. When the syllabus is the same, what is the difference between the examination? That is what we need to understand. For that purpose, suppose if this concept I take, derivation, the result is important for your board examination. So that preparation ends there. And afterwards, some more additional habitual things, which I call habitual things, because this should be your regular practice on your own, because teacher keep on telling you that look at RHS, LHS, what type of relation they bear, right? What type of changes are possible here and what not. Writing these ratios, writing the percentage changes, drawing graphs. When we do all these additional, when we cultivate this as a habit apart from the derivation, this what helps you for the other examination. So it's all about the set of habits that we have that decides our performance in the examination, right? And that is why CET preparation, NEET preparation or JEE preparation is not something that you do after the completion of syllabus. Many teachers will tell you that let the syllabus be finished, afterwards we do coaching and all. See, I am telling you, it is not possible afterwards. This should be your regular habit. This is how you look at the things every day. If you practice this, then coaching teacher will help you in a different way. Then you can just move ahead. So remember, derivation is over. After that, you please make all these note points and practice it once, twice. And after that, you make your own observations. Call your teacher, speak to the teacher. This is what I expect you from you. Because since it's only 2 hours of classes per day, 2 subjects per day happening with you, right? 2 subjects and 2 hours class. After that, all the 22 hours is with you. So whoever is very sincere, committed student, definitely I do expect they do this. Somebody may call it as extra work. No, this is what is actual work. Because up to this point, it is not your brain that has used it, is it? And somebody has told you and you have just duplicated that. So this is not extra job. This is what is your correct job. Duty, responsibility. I wish you do that. Okay. In my next board, I would like to show some more results. See, we have done the case of definition of potential itself, is it not? Now, this is the time I take that definition one more time. And let us see how many things that we can pick from that fundamental definition. See, this is our fundamental, the definition of potential. Vp minus Vq, potential difference between the 2 points P and Q. W, Q to P, every time I have to know that order is important. Move from the point Q to P, then you are writing Vp minus Vq is equal to, because this is initial and this is final. So that is how we are writing it as Vp minus Vq is equal to. And supposing one point is inside and the other point is outside, right? Suppose if the initial point is outside, then simply we call it as potential at that point, right? Potential difference or potential difference between 2 points or potential difference at a point. At a point is also a difference with respect to infinity, where the potential is 0, right? Now, supposing if I write it as V is equal to W by Q. Generally, every time instead of writing Vp minus Vq, Wq to P, suppose if I represent this expression like this, the same expression I'm writing like this, then what happens? This W is equal to Vq. W is equal to Vq. Nothing but the definition of potential itself is a very big tool for us in all the numericals. Yes, maybe numerical or conceptual, whatever it is. Now, what are the key terms this expression now will throw light on? Q is the charge. Q is the charge. It can be positive charge or negative charge, remember. If Q, a charge, is displaced between 2 points like this, I have told Q to P, right? If Q is a charge, of course a point charge, Q is a point charge moved between 2 points in an electric field, then the work done in moving that charge is given by V, the potential difference between the 2 points times magnitude of the charge. Is it not? So this is what is a fundamental but big tool, I tell you. Now here comes, because for board examinations or any other examinations, in the case of board examination it can be the simplest. Even the other cases also simpler if we have the right idea about what we have discussed about for 1 hour. What is meant by work, positive work, negative work. And after that, following this order, whether it is moved from P to Q or Q to P, whether it is positive charge or negative charge, all these things when combined, we get different results. And that is what is the specialty in the case of NEET or CET or any other examinations. What are those special cases or what are those interesting results? See here, because this work can be positive or negative, this V can be positive or negative, Q can be positive or negative, and a whole lot of things are there, is it not? First I am writing it as, first let me take up one situation I showed. Suppose this is the electric field. Of course electric field is there, right? So this is an electric field. And supposing this is some point P and this is some point Q, the two different points. Now let us take up this example and see what are the different possibilities are there to understand. Few things I will few things like 2 1 ja 2, 3 1 ja 3. I will tell you afterwards. You please make it as 4 1 ja, 100 1 ja, 10 1 ja. You do that. P to Q. This is electric field. The first point you remember, when we have told the relation between field and potential, the significance with respect to the negative sign, we have told that in the direction of a field, potential always decreases. That is, the points which appear earlier at higher potential, the points which appear later in the direction, right? They will be at lower potential. In this case, what happens, you tell me? The result is Vp greater than Vq for this particular case. So when a field is given and you are given two different positions, first you look at the positions, PQ or AB, whatever the positions that you have named, look at those positions and identify where the potential is higher or lower potentials. How do you get that higher potential or lower potential? Two things. Both are common sense. One thing is with respect to distance. Earlier also we have seen that V proportional to 1 by R is there, is it not? V proportional to 1 by R, therefore in some cases we will use this common sense, that more distance, lesser potential, like that. Or else this one I have told you, in the direction of field, potential decreases, therefore P is at higher potential, Q is at lower potential. And sometimes, and one more important thing that arises is potential due to positive. Every time we are telling about the positive charge. Supposing here I take a positive charge plus Q. This is some point P and this is some point Q. This is at a distance R1, okay, and this is at a distance point Q at a distance R2. Now this is a positive charge, remember, and therefore potential is also positive. Therefore here V proportional to 1 by R result you will use such that what you write is V at P greater than V at Q. Yes, it is valid. Why? Because this is supposing plus 5 volt you will get it as some plus 3 plus 2.7 something like that, the number you will get. Therefore Vp greater than Vq is valid. So the situation is right for this given situation. For this given situation, what is that? Q is the charge, a positive charge. P1 or P position, here comes the Q position. This is R1 and this is R2. This is valid. Whereas, see, this is supposing a negative charge, minus Q. And one more time I have the positions P and Q at distances R1 and R2. In this example, tell me, in this example, clearly 1 by R1 greater than 1 by R2. Does it mean that V at P greater than V at Q? Can you tell that? No, because here comes the negative sign. Here comes negative sign. Earlier we have told, supposing if this is what is plus 5 volts and at Q if I write it as plus 3.6 volts, then 5 and 3.6, the numbers along with the sign we have used actually, therefore this is higher, plus 5 greater than plus 3.6. Whereas here you see, supposing at this point be the same, plus, in fact it is negative potential, is it not? The negative charge and negative potential, therefore if this is what is the point P where it is minus 5 volts and at Q supposing it is minus 3.6 volts, go back, go back to your primary courses where we have said that number, line and all, where you will see that this minus 5 and minus 3.6, what does it mean? This is lesser value or little higher value. Is it not? Therefore, when you are comparing the potentials at two different points, there are whole lots of things to be taken care of. Supposing if it is such case, we will make use of this. Or else, some point charge is given or other charges are given. There what you need to find, whether it is due to positive charge or negative charge. In the case of positive charge, we can directly use that V proportional to 1 by R. More distance, lesser potential, lesser distance, more potential. Whereas negative charges that they are given, exactly the cases will be reverse of that. So here, V proportional to 1 by R should be understood there not only with this one but also with respect to Q also. And therefore here number of different cases now will arise. And all this makes a difference of positive value or negative value. You may get it as some minus 0.5 or plus 0.5, that makes the difference. And that is why I am discussing this as a special case. Now, remember this higher potential, lower potential, that is always with respect to positive sign, negative sign. Every aspect is important here. Now, see how intelligent this is. This is how you will use your brain. All the other cases it is only duplication. Teacher ಏನು ಹೇಳ್ತಾರೆ as it is ನಾವು by heart ಮಾಡಿ ಬರೀತೀವಿ. We have not used any of our brain. ನಮ್ಮ ತಲೆ ಓಡಿಸಿದ್ದು ಏನೂ ಇಲ್ಲ. Simply duplication, copying ಮಾಡಿದ್ದೀವಿ. ಇವಾಗ ನೀವು ನಿಮ್ಮ ಬ್ರೈನ್ ಯೂಸ್ ಮಾಡಬೇಕಂದ್ರೆ this is what is a fish. ಈ ತರ ಬಂದು every time you have to use your brain. What is that? W is equal to VQ. Let me now discuss some cases. W equal to VQ. I am writing as case 1. What is case 1? Positive charge. Positive charge moved from higher potential to lower potential. Higher potential to lower potential. Supposing if this is what is the case, then what happens? Here Q is positive. Remember, moved from higher potential to lower potential, it is moved. Higher to lower potential it is moved. In such case, what happens? This W is equal to positive, W greater than 0. W greater than 0. W greater than 0 you will get. You use all these statements. Vp minus Vq, Wq to P, we said, right? Then what is that? Vw by Q, W is equal to Vq says W greater than 0. What is positive? Yavaga. Nodippa ಎಲ್ಲರೂ. Positive charge moved from higher potential to lower potential. Then work is always positive. Work is always positive. Therefore, what is the case 2 that arises? Case 2 arises, positive charge moved, displaced from, yes, lower potential to higher potential. Lower to higher potential, that is against the field. Higher potential to lower potential means along the field you will get, is it not? The displacement is along the field, here the displacement is opposite to the field. Combine all our previous results, you will get, and this definition also tells you that work done is less than 0, negative work, positive work, negative work. For positive charge I have told you. Therefore, for what happens to negative charge, you can write it the case 3 and case 4. Right? I have taken the case of positive charge, you do it for negative charge. Yes, at least you do that. This is also a duplication. Exactly opposite results that you get, isn't it? Negative charge displaced from higher potential to lower potential. Work is negative, whereas negative displaced from higher potential, lower to higher potential, work will be positive. Now here, when you are doing those the J examples, here one more important point I would like to tell you that work positive. You remember we have said that dW is equal to minus of du. An important thing you remember, right? Therefore, dW is equal to minus du result. If you remember, work greater than 0 means, work positive means potential energy decreases. This is the consequence. Work negative means potential energy increases is this outcome that we have to understand. In physics, we know that always work and energy are interrelated, is it not? And therefore, here the potential energy decreases, and in this case, potential energy increases. For positive charge, I have taken, please negative charge, you write that. And one more time, see, one more time, what is that? Because this is an important concept. This concept will be the fundamental, the basic for our next unit, what we call current electricity. In after once we finish this electrostatics, that is a discussion of the charges at rest, which we are talking about. And then in the second part, we begin with that current electricity, moving charges. This becomes the fundamental, and that is why watch it carefully. And I'm telling you, most of the students never look at these results and they never bother about these results. But if you are a very sincere and committed student, you please go through all these results. Practice them once, twice, thrice. Now, again we told, remember, with respect to the field, we told that positive charge. If, suppose I'm telling you, if a charge if a charge is placed, if a charge is placed in an electric field, what we told, remember, the same the case of projection also. First, let me take this as a fundamental concept to tell you one more important statement. Charge placed in an electric field, we have told positive charge accelerates parallel to E bar. Positive charge accelerates parallel to E bar, that is along the field. And now we have told that acceleration, let me tell, along E bar. Now we told that in the direction of field, potential decreases. So these are two statements we have seen independently with respect to force, and now here with respect to potential, the statement is in the direction of field, potential decreases. Right? Now I will combine these two results. What is that you get? So combined result will give you that I will write it as a big star mark, that positive charge tends to move, displace. It is its natural tendency. I am telling you, we are not using any external agency for that. The field will does that work, no external agency. Remember? So this plus Q tends to move from, higher potential to lower potential. Higher potential to lower potential. This is the natural direction for a positive charge. And therefore, automatically by default you can write it as negative charge always tends to move from lower potential to higher potential. So what are the natural tendencies of the charge in an electric field? Is that always a charge tends to displace on itself. Why it is displacing? Because of potential difference. So remember, when we are discussing about the stationary charges and introduce the concept of potential, the important point that you will make out is that for this stationary charge to get into motion, we need to create a potential difference such that positive charge always tends to move from higher potential to lower potential, and the negative charge always tends on its own to move from lower potential to higher potential. This is an important take, and all these things are so vital in your numericals when you do it for any type of examination. See, when we are talking, don't think that the teacher always speaks about a particular examination. Examination is a challenge, and examination is our responsibility. And our journey is, in this journey, examination is also one of the milestones. It is not the destiny. Therefore, to achieve that milestone, your teacher speaks about exam. Otherwise, remember, in our life journey, these are all the things where we are improving our personality, our ability of understanding the things. It is not simply preparing for the examination. This is all very vital for all your examinations, friends. Very, very important. Therefore, now you see. Now I can make one more important statement. This you should write in your notes. In the beginning, potential we have introduced as an analog of energy or work. So in electrostatics, wherever you get work or energy, immediately this concept of potential should come. Right? Keep it aside. Now, we will look at this potential in other way also. How? Remember, when you first year, topics like fluid mechanics, a fluid flow when you have taken, it is always, natural direction is higher pressure to lower pressure is the natural direction. It flows on its own. Supposing if you want to make the flow from lower potential to higher potential, yes, we need to work, we need to do work, that is we need to spend energy. That is what is there. There it was the flow of the fluid, now here it is the flow of charges. The direction of flow depends upon a particular parameter. In fluid mechanics, it depends upon the higher pressure, lower pressure concept. Similarly, in the case of heat transfer also, what is the direction of heat transfer? We said conduction, not the convection property. Conduction, what we said, from higher temperature to lower temperature is the natural direction of heat flow. If you want to reverse that, yes, again work need to be done. So in fluid mechanics, it was pressure difference. In heat transfer, the conduction, it was the temperature difference. Now here, the charge flow, what we need is potential difference. Therefore, this term potential, we also look it as an analog of temperature or pressure. Pressure difference, temperature difference, here comes potential difference. In such cases, what is the natural tendency? Higher to lower or lower to higher? Which charge is the important case in all our examples? Is it not? So I hope this kind of understanding after those two derivations, very important. Read it twice or thrice, make your own notes, and I do expect at least a couple of my Vijayarthi will call me and discuss about these results or even some more observation if you have make. Right? Thank you. Have a safe day. Have a good day. We'll meet tomorrow. Thank you. Good day.